Accelerating a standard military fighter jet past Mach 5 causes the airframe to liquefy. At these speeds, atmospheric friction reaches 2,000 degrees Celsius, turning structural metal into a shower of liquid droplets in seconds. For decades, the Lockheed F-104 defined the logic of supersonic speed. It utilized a razor-sharp, needle-like nose to part the air and minimize drag as it broke the sound barrier. Yet the Apollo capsules, designed to hit the atmosphere at Mach 25, discarded those sharp edges entirely. The fastest vehicle ever built by humans was shaped like a blunt, flat-faced block. This creates a direct conflict in aerospace logic. If sharp geometry is the key to speed, why is a blunt shape the only thing that survives the absolute fastest flights on record? Global powers are currently competing to build a new generation of maneuverable, reusable hypersonic vehicles. The hypersonic threshold begins at Mach 5, a velocity where a vehicle covers more than 1 mile every second. At these speeds, the standard principles of lift and drag that govern traditional aircraft become non-functional. To survive this environment, engineers had to reevaluate the physical behavior of gas molecules during high-speed compression. In supersonic flight, air behaves as an ideal gas, parting cleanly around sharp edges to create V-shaped shockwaves. At Mach 5, molecules can't move aside. They stack against the leading edge, compressing into a dense wall of matter. This compression creates a thin boundary layer where the vehicle's kinetic energy is converted into thermal energy, pushing surface temperatures past 2,000 degrees Celsius. This heat causes air molecules to dissociate, meaning they physically split apart and transform into a chemically reactive, glowing plasma. A hypersonic vehicle operates entirely within a self-generated envelope of liquid fire. Inside that plasma boundary layer, microscopic acoustic disturbances called Mach modes begin to oscillate. Mach modes are high-frequency pressure waves that develop uniquely in high-speed flows. Data from hypersonic quiet wind tunnels, specialized facilities that simulate high-speed flow without background vibration, reveal that these waves cluster into concentrated hot streaks. These hot streaks cause unpredictable spikes in heat transfer. They can incinerate a specific section of a hull while the surrounding structure remains intact. Subscribe to the channel for more deep dives into the engineering that makes the impossible possible. Standard aerodynamics cannot protect an airframe from these erratic plasma spikes. Survival requires a change in material science. The blunt geometry of a space capsule is a deliberate thermal strategy. A wide leading edge forces the superheated shockwave to detach and sit several inches in front of the vehicle. This creates a buffer zone of subsonic air between the plasma and the actual skin of the craft. Even with that buffer, the radiant heat would melt aluminum or titanium almost instantly. Engineers now use ultra-high temperature ceramics, or UHTCs. These are materials like hafnium diboride that maintain their structural integrity at 3,000 degrees Celsius. Because ceramics are brittle, they are woven into ceramic matrix composites, or CMCs. CMCs embed ceramic fibers within a ceramic matrix to provide the flexibility needed to withstand flight pressures without shattering. The latest self-healing composites incorporate compounds that react with oxygen mid-flight. If a microscopic crack forms, these compounds oxidize to seal themselves shut against heat. Mach 5 flight is as much a challenge of material science as it is of fluid dynamics. The Space Shuttle Discovery demonstrated that vehicles could withstand these temperatures repeatedly for over 30 years of operational service. The materials engineered for the hypersonic frontier are now solving engineering problems on the ground. Ceramics designed for Mach 5 leading edges are being integrated into next-generation nuclear reactors and high-efficiency solar grids to manage operational heat. The technology required to survive the upper atmosphere is making high-heat energy generation more efficient on Earth. We have moved from mastering basic aerodynamics to confronting the chemical and thermal chaos of the Mach 5 threshold. Advancing human transportation requires vehicles capable of navigating a sustained plasma environment. The atmosphere is no longer an obstacle. It is the testing ground for the materials that will define the next century of flight.